Thank you very much. It is my pleasure to start our summer school. I think that it must be a very helpful and fruitful event in stochastic process theory, not only in Jilin University and our Institute of Mathematics, but more widely spread. And the reason is the following. Today's mathematics has a very large gap between level of university education and complexity of real problems in modern mathematics. To make a bridge for young people, in this direction, such schools in different subjects in mathematics are organized. For subjects of our school, we choose the dynamics of complex objects. It can be a system of interacting particles. It can be particles which moves on as complex graphs, or some specially chosen trajectories of Brownian motion, or semi-groups which are related to non-classical diffusions. So I think that all the subjects are of great interest today in mathematics, and during our lectures, it will be very good to be familiar with these subjects, or to have a possibility to ask some questions. Moreover, I think that we will organize some discussions at the end of the school. So, from my point of view, this event must be interesting and fruitful. So, I have two wishes now. One is, as usual, I want to wish success to our event. But another one, I want to fix one mistake in the announcement, because in the announcement we have school in modern problem of stochastic process. My idea is the following: let us put the first school and make this tradition that next year it will be second school, and so on. So I wish success to all participants, and I wish you to have a great days and interesting discussions. Thank you very much.
Thank you, Professor Andrei. And also, I want to invite to say some introduction speech to Professor Shen. He's a professor from Jilin University. So please.
Okay, thank you. So good afternoon, everybody. First of all, on behalf of the School of Mathematics, I would like to extend a warm welcome to all the friends from abroad, teachers and students to attend this international summer school. Let me introduce a little bit of the city Changchun and Jilin University. Changchun is the capital of Jilin province and located at the northeast of China. It is 1,000 kilometers far away from Beijing. Jilin University is almost the biggest university in China, and there are more than 70,000 students. We have about 200 staff in the School of Mathematics, including 4 foreign postdoctors. School of Mathematics of Jilin University are open for international collaboration and exchange. I would like to take this opportunity to invite all the experts who participated in the school online to visit Jilin University in the future. Last but not the least, I would like to express my gratitude again to all the distinguished guests and participants present here at the opening ceremony. which all of you benefit a lot from the school. Thanks.
Thank you. So maybe it starts to our lectures, and it's my pleasure to introduce the first lecture of the today meeting. This is a lecture which is given by Gerogii Riabov. He is a researcher from National Academy of Science, and he will give lectures about stochastic flows and random dynamical systems. So please, do you need to share your screen?
Yes. I would like to share.
Yes, please. So,
Okay. Thank you for the introduction. I hope you can see my screen.
yes.
There will be a lecture about stochastic flows of solutions of smooth stochastic differential equations. I will say a few words about my plan of lectures. The main object of interest for me will be stochastic flows of maps of different state spaces. So by M, I will denote the state space. It will be at least a measurable space. In fact, in all examples, it will be a locally compact, separable metric space equipped with a Borel sigma field. The main example will be the Euclidean space. A lot of things that I will talk about will be valid for manifolds, though I will not touch this topic much. And also, in the end, we will look at stochastic flows on metric graphs. So from the most general point of view, a stochastic flow of maps is a family of random mappings of the state space. So we can imagine that we have some state space M, and a flow of mappings is just a collection of mappings from M to M that tells us how points move, like S and T, they have the meaning of time. So the mapping phi st tells us how the points move from time S to time T over state space. And the word stochastic means that these mappings are random. The most important properties of stochastic flows of maps are the flow property, which means that the composition of two mappings from the flow during that act during times from R to S and from S to T is equal to phi RT. Okay. When we consider disjoint intervals of time, like T0 less than T1 and so on less than T, and then mappings act independently, and on intervals of time of the same length, the distributions of the same. Later we will give the precise definition of what is a stochastic flow. Here these three properties are the most distinguishing ones. Okay, the first examples of stochastic flows. The first examples of stochastic flows, they originated from the study of dependence of solutions of stochastic differential equations from the initial conditions. And the first works in this direction were done by Gichman, Blagoveshensky, Freidlin, and then the theory of stochastic flows of solutions of stochastic differential equations was formed in the works of following authors: Priore, Bismuth, Elworthy, Carver-Hill, Ikeda, Watanabe, and so on. In my lectures, I will discuss the following questions. So, how to construct stochastic flows from solutions of stochastic differential equations. And we will construct stochastic flows of homeomorphisms. Also, we will relate random dynamical systems to such flows. And then we will turn our attention to non-homeomorphic stochastic flows. That is, we will discuss coalescing stochastic flows on the real line. We will also construct random dynamical systems for such flows and develop some theory like a duality theory for coalescing stochastic flows. And also we will discuss such flows on metric graphs. First two lectures, they will be based mainly on the works of Kuunita. So they are about stochastic flows of homeomorphisms. So we will look at stochastic differential equations, find solutions to these equations, and will prove that the solutions of stochastic differential equations with smooth enough coefficients, they produce stochastic flows of homeomorphisms. Okay, but first I think it is instructive to look at a non-stochastic situation. So assume that we have the Lipschitz vector field on Rd. Okay, so the increment of the field A is bounded by some constant times the increment of the argument. Here, by norm of Rd, we will understand the usual Euclidean norm. So this is sum of components squared. And let's consider the simple ordinary differential equation dxt equals a of xt dt. Then it is not hard to show, and we will show it that for every initial point x, there is a unique solution of the equation 1 with the initial condition x of 0 is equal to x small. We will denote this solution by phi t of x. So phi t of x is the position of the solution at time t when the solution is at point x at time 0. So in this notation, we can write that d phi t x over dt equals to a of phi t of x, and phi 0 of x is equal to x. It turns out that phi t is a homeomorphism of Rd, that phi t satisfies the flow property, meaning that composition of homeomorphisms phi t and phi s is equal to phi t plus s, and phi is continuous as a function of t and x. Phi t of x is called the flow of solutions of ordinary differential equation 1, and it is a convenient notion to describe the global picture which is related to this ordinary differential equation, in the sense that when we consider a flow of solutions, we consider the simultaneous behavior of solutions to ODE that start from all points of the space. So this is convenient to describe the long-term behavior of solutions, to discuss stability of solutions, to find some attractors, and so on. And the question we will be interested in this lecture, and I think in the next one, is can we expect the similar behavior for flow of solutions of a stochastic differential equation? But now let's see how we can find the flow of solutions in the non-stochastic case. We can write the equation in the integral form. So phi t of x is equal to initial condition x plus the integral of a of phi r of x dr. And to construct the solution, we can apply, for example, the contraction principle. Let's fix time t and some constant a, which is bigger than the Lipschitz constant of the coefficient. Then we can equip the space of continuous functions on minus t with values in Rd with the following metric. So this is this metric is equivalent to the uniform metric, and let's consider a mapping that takes a continuous function f and transforms it into a continuous function x plus integral of a of f. Then we can check that this mapping f capital is a contraction mapping. So if we take two continuous functions f and g, apply f capital to these functions and look at the difference, then this is just the integral of the difference afr minus agr, and we can estimate it by Lipschitz condition. So the increment of a is estimated as L times the increment fr minus gr. Okay, and this quantity, by definition of the metric, is not greater than exponent ar times the distance between f and. Okay, after integration, we get this estimate. What remains is to divide by this exponent, take supremum, and we see that the distance between f and fg is estimated as L over A, distance between f and g. So we have a contraction mapping, which immediately gives us existence of a unique continuous function that satisfies equation 2. Moreover, from the contraction principle, we know that iterations of the mapping f, they converge to this function phi. So if we define phi 0 of x as x, and then the next iteration phi n plus 1 is the action of f on phi n, then we know that uniformly these iterations converge to the fixed point phi. In fact, we can now show that this convergence is uniform in t and in x. So let's consider initial conditions x from some compact set. So here x belongs to a ball with the radius, some radius k. If we denote this constant by b, then by induction we can show that the uniform uniformly over x from this ball, the distance between iterations phi n and phi n plus 1 is estimated by this quantity. So when n is equal to 0, it is just the definition of b, and for other values of n, we can just know that the difference between phi t n plus 1 and phi t n is the integral of a phi n r minus a phi n minus 1 r, and then we estimate it as the Lipschitz constant L times the difference between phi n and phi n minus 1. So what we will do, we will integrate this expression LT to the power n minus 1 over n minus 1 factorial. We will integrate it from 0 to t. Okay, so we will get LT to the power n divided by n factorial. So from this estimate, we see that the following series is convergent. In particular, phi n converges to phi uniformly in t and x, so phi is continuous in t and x. And finally, we observe the following relation. So phi s plus t of x. This is x plus integral from 0 to s plus t, which we can write as integral from 0 to s a of phi r of x dr plus integral from s to s plus t, which is the same as integral from 0 to t a of phi s plus r of x dr. So we get the following equality, which says that phi s plus t as a function of t is a solution to our ordinary differential equation with the initial condition phi s of x, which means that phi s plus t is equal to the composition phi t and phi s. Also note that we have solved the equation like on the real line. So for t bigger than 0 and for t less than 0, since phi of 0 is obviously identity, we immediately get that phi minus t is the inverse of phi of t. So we have a homeomorphic property of phi t, and we get a flow of homeomorphisms that consist of solutions of an ordinary differential equation. Okay, now let's go to stochastic differential equations. Again, we will assume that A and B are Lipschitz. Now A is the coefficient near dt, as in ordinary differential equation. And we will also add one term, the so-called diffusive term. So it will be B of xt times dwt, where W is a Brownian motion. This stochastic differential equation, it is not a differential equation in the usual sense, because the expression dwt actually, well, it makes no sense for every realization of a Brownian motion, because it is well known that trajectories of Brownian motion are of unbounded variation. In the sense that if we take a partition of the interval, let's say from 0 to 1, and compute the sum of absolute values of increments of the Brownian motion, then this sum will converge to infinity, let's say in probability, when the mesh of the partition goes to 0. Okay, so it is not the usual differential equation, and the proper way to understand this equation is in its integral form, because it turns out that the integral with respect to the Brownian motion can be defined rigorously for a special class of integrands, in particular for special type of processes X. And again, this is not the usual integral, and this makes a difference between the theory of stochastic differential equations and the theory of ordinary differential equations. Okay, stochastic integrals with respect to Brownian motion, they can be defined using the martingale theory. So I will quote some results from this theory. We will assume that omega fp is a complete probability space, that it has a filtration that satisfies usual conditions. Well, it is not so important what it means, but it means that the filtration is right continuous and completed by all sets of probability 0. A continuous martingale is a continuous process which is integrable, adapted to the filtration, and satisfies the following equality. So the conditional expectation of MT with respect to sigma field Fs is almost surely equal to Ms. With every filtration, we can associate stopping times that are random variables with this property. So here I will go pretty fast, because we will just use some properties of martingales. When we work with stochastic integrals, it is useful to consider local martingales. These are processes xt such that they are continuous martingales when they are stopped at some sequence, at some stopping times that increase to infinity. So if we can stop the process and get a martingale in such a way that these stopping times can be organized increasing to infinity, then we have a local martingale. And actually, a lot of properties of martingales, they extend to local martingales. And in fact, if we have a continuous local martingale which is integrable in the following sense, then it is a martingale. Okay, and the important property of continuous local martingales is the existence of a quadratic variation. It can be defined as a continuous adapted increasing process such that the difference between m square and this process m is a local martingale. The term quadratic variation can be explained by the following result. The quadratic variation can be obtained as a uniform limit in probability of such continuous processes. So here we consider the partition of the segment 0t and compute the sum of increments squared. So in fact, one can show that the only continuous local martingale which has a finite variation, yeah, so if let's say if the supremum of increments is finite, the only continuous local martingale with this property is a constant process. So there are no non-trivial continuous local martingales with finite variation. However, they have a finite quadratic variation. And this property allows actually to define stochastic integrals. So we will be mostly interested in continuous adapted processes. For these processes, a continuous local martingale is defined as a limit in probability of the so-called Ito-Riemann sums. These sums they look very much like the Riemann sums for the Riemann integral. However, in the last in all terms, we observe that we take the value of the integrand in the left point of each segment. So due to this definition, due to the martingale property, and due to the existence of the quadratic variation, it follows that these sums, they have a limit. This limit is uniform in probability and is defined, and this limit is called the stochastic integral. In particular, by construction, the stochastic integral is a continuous local martingale. So we see that stochastic integrals and they make sense for integrands that are continuous and adapted processes. We will use the following result, that the stochastic integral has a quadratic variation equal to the integral of integrand f squared with respect to the quadratic variation of n. In the case of the Brownian motion, which is of course a continuous martingale, its quadratic variation is equal to t. In fact, we can find the quadratic variation of the stochastic integral with respect to the Brownian motion. Okay, no square here, but square on the right side. Yes, so the quadratic variation of the stochastic integral f dwr is equal to the integral of f squared dr. And I will need two inequalities for martingales, for continuous martingales. The first is Dup's inequality, and that says that the expectation of the supremum of the martingale to the power p bigger than 1 is estimated by a constant times the supremum of expectations of this martingale at the power p. Okay, so this is one inequality. And another is the Borg-Holder's inequality that says that for every p greater or equal to 2, there is a universal constant c such that expectation of the martingale to the power p is bounded by the constant times expectation of its quadratic variation to the power p over 2. Okay. And one more result that we will need is the Ito formula. So first of all, for the quadratic covariation of two continuous local martingales can be defined using this identity. Actually, this is a process of bounded variation such that the product mt and t minus quadratic covariation is a martingale. For two stochastic integrals, their quadratic covariation is computed as the integral of the product of the integrands. Okay, and Ito formula says the following. Assume that we have m processes xij such that each process xi is the sum of the integral of the usual integral of some alpha and the integral and the stochastic integral with respect to some local martingale mj. Then if we substitute these processes into a twice continuously differentiable function f, we can write this the resulting process again as a sum of the integrals of the usual Riemann integrals, of stochastic integrals, and of integrals with respect to joint quadratic covariation of martingales mj. So the integrals with respect to ds and dms are of the j's derivative of f times the corresponding coefficients alpha j and beta j, and the integral with respect to the joint covariation of mi and mj is of the second derivative of f times these coefficients beta I and beta j. So these are results from martingale theory that we will need. And now let's consider the stochastic differential equation and try to solve it. In this equation 3, W will be a Brownian motion on the real line. So this is a process with independent increments, and the distribution of It is a continuous process with independent increments, and the distribution of an increment is normal with mean 0 and variance t minus s. By FST, we will denote the sigma field generated by increments of this process W from time s to time t. And from our definition of the stochastic integral, we can understand how to define a solution of the stochastic differential equation. So it will be an adapted continuous process such that with probability 1, for all t greater or equal to s, we have the following equality. Now, in this equality, all integrals are well defined. However, we saw that the stochastic integral is defined only as a limit in probability. As a result, we cannot expect the uniqueness of the solution of stochastic differential equation for all realizations of Brownian motion. If we take another continuous process, which is almost surely coincides with x, then this process also will be a solution of the stochastic differential equation, simply because the stochastic integral for tilde x almost surely coincides with the stochastic integral for x. So such processes are called indistinguishable. What we can expect is that we can look for solutions of stochastic differential equations up to indistinguishability. Now let's once again underline the difference with the ordinary differential equations. So assume that we are able to solve the stochastic differential equations for all initial data Sx. Yeah, so assume that for each S and X, we have a unique continuous adapted process, phi st of x, that solves the stochastic differential equation 3. Yeah, this one in the following sense. First of all, if we want to get a flow of mappings, we need to consider the composition. Yeah, so we substitute the random variable phi rs of x into the random mapping phi st of x. So this expression makes sense at least when this random mapping is measurable in x. So we already need to find the good modification of this process if we look at it as a process of S, T, and X. Secondly, if we fix R less than S and fix some X, we can write the solution after time S in the following form. So this is phi rs of x and plus the integral of a plus the stochastic integral of b. Even if we give sense to this expression, then we see that phi rt of x is a solution of the stochastic differential equation with the initial condition phi rs of x. So we can deduce that it coincides with this composition. However, as we saw, the solution is unique up to indistinguishability. It means that almost surely after time s, these processes coincide. However, the event where they may not coincide, this event depends on rs and x. So if we denote this exceptional event by, let's say, n rsx, then we will get a flow of solutions for free on the event which is the union of the complement of the union of all these exceptional sets. But obviously this union is uncountable, so we cannot guarantee that the composition of mappings almost surely will be equal to the mapping phi rt. And one more issue is that in the definition of stochastic integrals, the integrand must be an adapted process. As a result, when we fix initial data Sx, we solve the equation for t greater or equal to s. In the case of ordinary differential equations, we solved it for all t, and we easily got the homeomorphic property. So here, we will see that homeomorphic property of this flow is not immediate. Okay, now we even don't have a flow, but we will surely. So my next aim will be to construct a flow. So indeed, we will see that phi st x has a modification which is continuous in st and x, which is a flow, and which is actually homeomorphic in x. So this will be my next aim. So let's start with the modification of phi. No, let's start with the existence of the solutions of stochastic differential equations. So we have the stochastic differential equation 3. I recall that a and b are Lipschitz functions. L is the Lipschitz constant. And our first result will be to show that for any initial data Sx, the solution of stochastic differential equation exists and is unique up to indistinguishability. Similarly to the case of ordinary differential equations, we will find this solution by successive iterations. So define x0 just as x and xn plus 1 as the equation applied to xn. Yes, so this is x plus integral of axn dr plus stochastic integral of bxn dwr. And we will prove existence and uniqueness by estimating such quantities. So here p is fixed, p greater or equal to 2. We will estimate the expectation of the uniform expectation of the uniform distance between xn plus 1 and xn in the power p, and a uniform over some segment from S to T. So first of all, note that R0 is this quantity, and it is a finite quantity because the supremum of Brownian motion has all moments. So expectation of the supremum of the Brownian motion to any power p is finite. Yeah, and okay, and also we will use this simple estimate many times. So here we have the sum in the power p. We estimate it as the number of summons in the power p minus 1 times the summons to the power p, which is Hölder inequality. Okay, so rho 0 is finite. What about rho n? Again, let's estimate the supremum of the difference between xn plus 1 and xn as follows. So we just substitute the definition of xn plus 1 and xn. Yes, and we get constants. Here will be the first is a supremum of integrals of difference of a, xn minus 1, and a supremum of stochastic integrals of difference bxn and bxn minus 1. The first integral, where we have the difference of a, again, it is estimated using Hölder inequality. Yes, so this is the length of the interval to the power p over q. Q is the conjugate of p, which is p over p minus 1. Then we also put the norm inside the integral and estimate it using the Lipschitz constant, and get this expression. In particular, let's note that when we take supremum in R, this will be less or equal than some constant times the integral, and here the difference xn and xn minus 1 to the power p, we will just bound by rho n minus 1 of u du. After taking expectations. Yes, so here we have expectation of the supremum in R of this quantity less than c times the integral of rho n minus 1. And the stochastic integrals are estimated in a few steps. So first of all, we recall that stochastic integral is a martingale. So expectation of the supremum into the power p yeah, so here we just pass from vector valued martingale to the R valued martingale. Yeah, so bj is the jth component of function b. Now, using Dup's inequality, we estimate expectation of the supremum by this constant expectation of integral from s to t to the power p. Then we use Burkholder inequality and get expectation of the quadratic variation of the stochastic integral to the power p over 2. And then we proceed as in the case with A. So we estimate the increment of B using the Lipschitz constant, and again put p over 2 inside the integral and get this additional multiple. So once again we get a constant times the integral. This can be estimated by rho n minus 1 of u. So we proved that for some constant c, rho n of t is less or equal than c times the integral of rho n minus 1. Then we can iterate this. We can iterate this inequality and get by induction that rho n is bounded by finite constant rho 0 times multiples of the type Cn ts t minus s to the power n over n for factorial. So hence we get a convergent series which shows that in LP uniformly over segments xn processes xn have a limit, which is a continuous adapted process x. The convergence holds uniformly in all LP when p is great. Okay, in all LP, and recall that xn of t, xn plus 1 of t is equal to x plus the integral from s to t, a xn r dr plus stochastic integral bx and r dwr, and the left-hand side converges to x of t. What about the right-hand side? Convergence of the usual integral is simple. Convergence of the stochastic integral is also, I think, must be clear, because we just need to show that this stochastic integral converges to the stochastic integral of b of x. We consider the difference between bx dwr and proceed as before. So we take expectation, use Burkholder inequality, get rid of b, yes, and use this estimate, and use the convergence of expectation of xn to x. So I leave it as an exercise to show that stochastic integrals bxn converge to stochastic integral of b of x, and as a result, we show that the process x is indeed a solution of our stochastic differential equation. What about uniqueness? If we assume that x tilde is another solution of stochastic differential equation, if we assume that it is integrable in the power p, then it will be simpler to show that x and x tilde coincide. However, we do not know a priori that x tilde is integrable. To overcome this, we introduce stopping times Tn. Tn is just the first time when one of processes x or x tilde become greater than n. So we stop these processes at time Tn, and we consider the uniform difference between stopped processes to the power p. Then again, we can adapt all previous estimates to show that rho of t is bounded by some constant times the integral of rho of rdr. These bounds, they will be completely the same as in this proof. However, we will not have rho n. Now all rho n are equal. Okay, since rho of 0 is equal to 0, the Gronwall inequality implies that rho is 0, which means that almost surely solutions x and x tilde are equal. So we have the unique up to indistinguishability solution of the stochastic differential equation. We will denote it by phi st of x. Yeah, so it is a continuous process in t, as x is the initial data, and our next aim will be to find a continuous modification of this process in variables st and x. We will do this using Kolmogorov theorem, which says the following. So if we have a stochastic process, it can be a stochastic process with values in the Banach space. This stochastic process is indexed by a d-dimensional cube. If we can bound the increment of this process to the power gamma by some constant times the increment of arguments to the power greater than d, then the process has a continuous modification. In the case of our solutions of stochastic differential equations, we will get an estimate of the following form. So expectation of the increment phi stx and phi s prime t prime x prime to the power p. We will bound it as some constant times the increment of x prime to the power p times increments t prime and s prime to the power p over 2 with some multiple that depends on the size of x and x prime. We will get this estimate for all stx, where s and t vary through the closed segment x and x prime in Rd. And I think we will do it next time. Actually, we will use the same technique of estimating expectations of integrals and stochastic integrals using Burkholder inequality, and also we will use the Ito lemma. So this will be the program for tomorrow's lecture. So we will construct a continuous modification of phi. We will prove that this continuous modification is a flow of homeomorphisms. And actually, we will even improve this result and find a random dynamical system for this flow. And for today, I think we can finish. Thank you for the attention.
Thank you very much. Maybe some of participants have questions or some comments. Please ask, don't hesitate to have some questions. Okay, I think that no questions for today. So thank you once more. And I want to announce that we will have the second lecture after like 23 minutes. So please have a break now and see you. So in Chinese time, it will be 3:30 p.m. and hope to see you here again.